Now in the previous lecture we have learned how can we search for a node in a binary search tree. Now in this lecture we will talk about how can we delete a node from binary search tree. Now in this case, when we want to delete a node from binary search tree, we have three cases. The first case is the node to be deleted is a leaf node. And the second case is the node has one child. And the third case is the node has two children. So let's look at all of these three cases one by one. Now the first case is that we want to delete a node which is a leaf node. So let's say we have a binary search tree like this and we want to delete a leaf node of 40 from this binary search tree over here. Now the first thing that we are going to do, we need to find this node. So to find this node over here, we are going to start from the root node. We are going to compare 40 with root node. We see that 40 is less than root node. We are going to continue to the left subtree. Then in the left subtree we have 50. So we are going to compare 40 with 50. We see that 40 is less than 50. So this means that we are going to continue to one more step to the left subtree. So in the left subtree over here we have, so one more time we are going to compare 30 with 40. So we see that 40 is greater than 30. So this means that we are going to continue to the right child. So in the right child, we see that the 40 is located over here. So this means that we are going to just delete this node from this binary search tree over here. Now with this, we have successfully deleted a node, which is a leaf node in binary search tree. So with this, we have completed the first case. Now the second case is we want to delete a node which has one child. For example, if we want to delete 30 over here, one more time we need to find the 30 in our binary search tree. So this means that we are going to compare 30 with the root node. So in this case we see that 30 is less than 70. So this means that we are going to continue to the left child. So in the left child we have 50. So this means that we are going to continue to the one more time left child because 30 is less than 50. Now here we have found that 30 is located over here. And for 30 we have child of 20 over here. Now in this case, all we have to do is connect a child of 30, which is 20, with the parent of 30 over here. So in this case, if we delete 30 from here, we are going to connect 20 with the parent of 30 over here. So the parent of 30 was 50, so this means that's going to be added as a left child over here. So if it is left child, so we are adding it as a left child over here. Now with this, we have successfully deleted a node in which we have only one child. Now let's continue the third case in which we have two children for the node that we want to delete. So let's say we have a binary tree like this and we want to delete a root node from this binary tree over here. Now in this case we see that for the root node we have two children. So for these children we have also children. So let's see how can we delete root node from this binary search tree over here. Now here the first thing that we need to do, we need to find the successor of this node over here. Now in our case the successor of this 7th over here is 80. Now you might be interested, how do you find it? It's basically the smallest node in the right subtree. So this means that if you want to find a successor of a root node in case of binary search tree, we need to find the smallest node in the right subtree. Now if you look at this tree over here, you can see that the smallest node in the right subtree is 80. Now after finding the successor of node, we need to replace the value of node that we want to delete with the value of successor. So in this case, we are going to update to the place of 70, 80, because the successor is 80. Then we are going to delete 80 from here. So in this case, 80 is left child of the 90. So this means that if we delete 80 from here, the child of 80 will be the left child of 90 in this case. So after deletion, the 85 will move as a left child of this 90 over here. Now with this, we have successfully deleted a node in which we have two children. Now this is how deletion of a node in case of binary search tree works. Now based on this logic over here, let's head over to Java and create delete node method in practice. Now inside this binary search tree class, we are going to create our delete method. Now before creating delete method, we need to create a method which is finding the successor of given node. So we know that the successor of given node is the minimum element in the right child. So here I'm going to declare our method like this. So it's going to be like this, public static. So the return type, it's obvious that will be a binary node because we need to find the minimum node. And the name of method will be minimum node. And as a parameter, it's going to take root, binary node, root. Now here, how can we find the minimum element? Now we know that the elements that are less than root node are located at the left subtree and the elements that are greater than root node are located at the right subtree. So this means that we need to search for a minimum element in the left subtree. So I'm going to check that. If the left child is null, in this case we are going to return that node, root node, and if it is not null, in this case we are going to call this minimum node method recursively for the left child. So it's going to be like this. If root.left is equal to null, so this is basically our base condition. In this case we are going to return null because in this case we don't have any left child. So the node that we are in will be the minimum node. So I'm going to return root from this parameter. Otherwise, in the else condition, we are going to call minimum node method recursively for left child, because as we know, the elements that are less than root node are located at the left child. So I'm going to call it for left subtree. Now with this, we have successfully implemented our minimum node method. Now we are going to use this minimum node method in the deletion method that we are going to create over here. So under this method, I'm going to create delete node method. So it's going to be like this. So here, this method also will return the type of the binary node. In this case, we are going to return the node that we are deleting from the binary search tree. So in this case, it's going to be like this: binary node, delete node. So here again, it will take two parameters. The first parameter will be the root parameter, and the second parameter, the value that we want to delete from this binary search tree. So in this case, root parameter will be the type of binary node, and the value that we want to delete will be the type of integer, because our binary search tree is integer binary search tree. Now the first thing that we are going to do over here is we are going to check that if root node is equal to null, this means that we have searched all nodes in this binary search tree and we couldn't find the value that we want to delete. In this case, this means that the value not found in binary search tree. So that's why I'm going to put it if condition like this: if root is equal to null. Basically here, root is the value that comes from this parameter, root parameter over here. So in this case, we are going to print out saying that the value not found in the system. So it's going to be like this: system.out print value not found in binary search tree. Now then, after doing so, we are going to return null, because in this case we are not deleting any node from this binary search tree over here. Now then, we are going to write another if condition like this: if the value that we want to delete is less than this root's value, in this case we are going to call this delete node method recursively for left child. Otherwise, if it is greater than the root node, this root's value, in this case we are going to call it for right child. So here I'm going to write if condition like this: if value is less than root.value, in this case we are going to set root.left is equal to, we are going to call this delete node method for root.left, and the second parameter in this case will be value. Now after doing so, in the else if condition, we are going to check that else if value is greater than the root value. In this case, it means that the value that we want to delete is located at the right subtree. So we are going to call it for right subtree. So root.right is equal to delete node and the parameter root.right and value. Now with these two recursive calls, we are looking for the node that we want to delete, and after finding it, we are going to implement the logic over here inside this else condition. Now here, in the else condition, we are going to write the cases that if the current node is the node that we want to delete. So as I said before, in this case we have three cases. The current node is the leaf node, the current node has one child, and the current node has two children. So this means that we have to implement these three cases inside this else condition over here. So here, the first thing that I'm going to implement is if the current node has two children. So how can we check that if the current node has two children? So we can do it like this: if root.left is not equal to null and root.right is not equal to null, in this case it means that in the current node we have left and right children. So this means that we want to delete a root node in this case, and in this case we have two children for this node that we want to delete. So what we are going to do over here is we are going to create a temporary node which will take the value of root, which is the current node. Then we are going to find the minimum element from the right subtree. Then we are going to set root's value to the minimum node that we are finding from the right, and then we are going to call this delete method for the minimum node's value. So in this case it's going to be like this: first we are creating a temporary node. It's going to be the type of binary node, in which we will have present node, which is root in this case. So then we are going to find the minimum element from the right subtree, because in case if we have two children for a node that we want to delete, in this case we are looking for the successor of this node. So successor is located at the right subtree, which is minimum element at the right subtree. So that's why we are going to call this method minimum method that we created over here for the right subtree of this current node over here. So it's going to be like this: binary node, minimum node for write. So I'm going to name this variable for write, and it's going to equal to minimum node. We are going to call it temp.write, because in this case, in the temporary node, we have current node's value, so we are going to call it for write. Now, after doing so, we are going to change the root's value to the value that we are getting from this method. So it's going to be like this: root.value is equal to minimum node for write.value. Now with this, we are taking the successor of the node that we want to delete and put its value to the value that we want to delete. Now then, after doing so, we need to delete minimum node from the write subtree. So this means that I'm going to call this delete method for the write subtree. So it's going to be like this: root write is equal to delete node. So in this case, we are going to call it for the write child, because in this case, the minimum element is located at the write child, and the value will be minimum node dot value. So we need to delete the successor from this write subtree over here. Now, after implementing it, with these lines of code over here, we have implemented logic in which we have two children for the node that we want to delete. Now let's continue to the second case, in which we have one child. So in this case, we are going to implement the case like this: if the node that we want to delete has only left child, we are going to delete the left child. If the node that we want to delete has only the right child, we are going to delete the right child. So it's going to be like this: if root.left is not equal to null, in this case, we need to set the left child of the current node to the root's left. So in this case, it's going to be like this: root is equal to root.left, because we are going to delete the root node, so we are setting root node to the left root node. So this left child becomes the root node's parent's child with this line of code over here. Now in the else if condition, we are going to check that if the root node's right child is not null, we are going to do the same operation for the right child. So it's going to be like this: if root.right is not equal to null, so we are going to set root is equal to root.right child. So in this case, it's deleting the right child of the root and setting this right child as a root's parent's child. Then at the end, if the node that we want to delete is a leaf node, in this case, we are just going to set that node to the null. So in this case, in the else condition, we are going to put it root is equal to null. Now after deleting everything, we are going to return root node. So with this, we have successfully implemented a method which is deleting a node from binary search tree. So here we have implemented three cases. So in the first case, we have two children for a node and we want to delete it. And in the second case, we have only one children for a node and we want to delete it. And in the third case, the node that we want to delete is a leaf node. So we have implemented all three cases in this method over here. Now let's see how this is working in practice. So inside main Java class, so first I'm going to delete a leaf node. So I'm just going to call this delete method for the binary tree that we created over here. Then after doing so, I'm going to call leveler.traversal to see that if it is deleted or not. So let's run our code. Now after running, you will see that 40 is missing from this output over here. So this means that we have successfully deleted 40 over here. Now let's delete a node in which we have two children. So in this case, if I delete the value of 90, in this case for the 90 we have two children. So it's going to remove 90 from this binary search tree, and we are going to replace the value of 90 with the successor of the 90 in this case. So before calling this, I'm just going to call leveler.traversal before this delete method. Then I'm going to delete it and call leveler.traversal one more time to see the difference. Now here I'm putting print function to have a space between the output. Now if we run our code, you'll see that we have something wrong in our code because we have called to delete a 90, but 90 still exists over here. So if you go our method, you will see that for calling for right child, we have put value less than root value. So in this case, we know that if the value is greater than the root value, we are continuing to the right child. So here by mistake, I put less than, so it should be greater than. So if I fix it and run our code, you'll see that in this case, 90 gets deleted from this binary search tree. Now after running our code, you see that in the first output, 90 was the third element. In the second output, the 90 is missing. Instead of 90, we have successor of 90, which is 100 in this case. So with this, as you can see, we have successfully implemented deletion method in case of binary search tree. Now let's see what's the time and space complexity for this method over here. So as always, we are going to start from the first line of this method. So in the first line, we are checking that if the root node is equal to null. In this case, we are printing out to the console saying that the value not found, and we are returning null. So this part of code will take a one-time complexity. Then we are continuing to the next if conditions. In the next if condition, we are checking that if the value is less than the root value, we are calling delete node method recursively for left child. So this means that this line of code over here will take O(n) divided by 2 time complexity. Then in the else if condition, we are checking that if the value is greater than the root node's value, in this case we are calling one more time our method recursively for right child. So this method also will take O(n) divided by 2 time complexity. Now then, in the else condition, we have another if condition like this, in which we are checking that if the current node's left node and the right node are not null, in this case we are doing some operation over here. So this if condition standalone will take O(1) time complexity. Then inside this if condition, we are creating a node with the type of binary node and setting root node to this. So this will take O(1) time complexity. Then we are calling minimum node method and getting minimum value for the right child. So in this case, this line of code will take all again time complexity, because in this case we are only searching in the right child. So that's why the time complexity will be all again. So then we are setting minimum node's value to the root value. In this case, it will take O(1) time complexity. Then we are calling delete node method one more time for minimum node's value. So in this case, this will take also O(n) divided by 2 time complexity. Then in the else if condition, we are checking that if the current node's left child is not null, in this case we are setting root left to the root, and this part of code will take O(1) time complexity. Now similarly, we are doing same operation for the right child, so this part of code also will take O(1) time complexity. Then at the end, we are setting root node to null, so this one also will take O(1) time complexity. Now if we combine all these complexities over here, we will get all again time complexity. Now the space complexity is also all again, because in this case we are calling delete method recursively. So this means that it's going to insert some nodes to the stack memory for the next steps. So that's why the space complexity is also all again space complexity. Now with this, we have come to the end of this lecture. So in this lecture, we have implemented the logic to delete a node from binary search tree. So basically here we have implemented 3 cases. In the first case, the node that we want to delete is the leaf node, and in the second case, the node that we want to delete has one child, and in the third case, the node that we want to delete has 2 children. So all 3 cases are implemented successfully. So hopefully everything is clear about deletion of a node in binary search tree. So see you in the next lecture.